Hi students, today I am going to explain what is packing efficiency or what is close packing. So whatever they give, both are having the same meaning. Packing efficiency or close packing. We know what is packing. Yes, no? In a crystal structure, so the packing of constituent ions is done in such a way that they occupy maximum available space and they leave minimum space empty. So this is called close packing. So close packing or packing efficiency is nothing but in a crystal structure. So the packing will be like that. So it will be using all the available space. How much maximum it can use the available space by packing the ions, and it will leave very minimum space empty, and this type of packing is called close packing. It can be done in 3 dimensions. First we will see in first 1 dimension. Spheres are arranged in a row in a straight line touching each other. This is 1 dimension, and in 2 dimensions we can see by stacking the rows of closed packed sphere in 2 ways. So the 2 rows of 1 dimension rows of spheres, they are arranged in 2 ways. First one is square and second one is hexagonal. In square packing, what happens in this type of packing, the particles are arranged in adjacent rows and shows horizontal as well as vertical alignment to form a square. So when these are arranged so that they will form a square, when we see horizontally and vertically, we can see a square is formed, and it is having a type of row. So all the rows are similar to each other, and we can say this is a type row, and its coordination number is 4 because the center one is surrounded by 4. So coordination number is 4. Then what is hexagonal? Packing in every row are placed in depression between the particles of first row. So when we see the first row, so in the depressions, so in these two between these two, this is called depression. In this, one more circle is present, and in between these two again one more. So like this, in the depression of first row, second row is arranged so that it is called hexagonal, and we will get a hexagonal form. So, and first row is A and second row is B. Again third row is A, fourth row is B. Like this AB arrangement. So it is a AB type, and central sphere is in contact with 6 other rows, right? 1, 2, 3, 4, 5, 6. So the coordination number is 6 for this. And we talked about ions. What about the free spaces? The free space are called voids. How much efficiently it is arranged, we cannot escape from the empty spaces. Some free space will be there, and this free space are called voids. And what is packing efficiency? How much efficiently the packing is occurred, we can calculate. So packing efficiency is equal to percentage of total space filled by the particles. So when we take the full space, how much full space it is packed, how much percent it is packed, that is nothing but packing efficiency. That is equal to number of atoms per cell. For cell, number of atoms into volume of one atom by volume of a unit cell. So we take unit cell as a base and we calculate. So number of atoms per cell into volume of one atom by volume of unit cell. We can calculate the packing efficiency, and we can see the voids. What are voids? Free spaces. They are triangular in shape. We can see here they are triangular in shape. So when we see here, voids are free spaces. They are triangular in shape. They are having apexes upwards and some downwards. We can see their apex is upwards here, and in this they are having apexes downwards. So upwards and downwards apexes we can see. So this type of 2-dimensional close packing is very efficient form. Then next is 2 dimensions we saw. Next is 3-dimensional packing, close packing. From 2-dimensional hexagonal pack layers, we are making 3-dimensional. So by placing second layer over the first layer, so we keep second layer on the first layer. So over first layer, so layer A and layer B, and they will form 2 types of holes here. tetrahedral hole and octahedral hole. We'll see what is tetrahedral and what is octahedral. We'll just observe this. Here we can see tetrahedral holes. So we can observe one thing. The apex which is up is having tetrahedral holes, and the apex which is having down, they are having octahedral holes. So let's see what is tetrahedral holes and octahedral holes. See here. So tetrahedral voids are holes in the first layer are covered by spheres of second layer because a tetrahedron is formed. So here one first layer which is covered by a second layer, so that a tetrahedral hole is formed like this shape. Tetrahedral shape is there. So it is called tetrahedral hole or tetrahedral void. Then what is octahedral hole or octahedral void? We'll see. Triangular voids are in the second layer are above the triangular voids in the first layer. They are surrounded by 6 spheres. So octahedral voids. So triangular voids are in the second layer. So this second layer, they are above the triangular voids in the first layer. So what happens? They will form the 6. They are surrounded by 6 spheres. So it is a octahedral voids. Then when we see number of closed packed spheres be n. So for octahedral void it is n, and tetrahedral void it is 2n. Then placing third layer over second layer. We placed in the last one, we place the second layer over first layer. Next, that is over. After that, we are placing third layer over second layer, converting the tetrahedral void to HCP and converting octahedral void to CCP. We'll see what is HCP and CCP. So tetrahedral void of second layer are covered by spheres of third layer. We are covering the second layer with the third layer. So like this we can cover. So the second layers are covered by third layers. We are covering the tetrahedral holes and the octahedral holes. So we are covering the tetrahedral voids, and the pattern is, we can see layers is AB alternative layer. So it is a hexagonal close packing. So because it is a hexagonal form, it is a hexagonal close packing structure. In metals like magnesium and zinc, we can see this hexagonal close packing. When the third layer is placed above the second layer, which is covering the octahedral void, they are not aligned into A and B. So they are called C type. Again we will take one more layer. When the fourth layer is placed in this alignment, then we will get cubic closed packing structure or face centered cubic structure, we can say. And there will be ABC, ABC, ABC like this. We can see the cubic closed packing structure, and metals like copper and silver will be formed by these structures. And they are very highly efficient, and 74% of space is filled. When we calculate the packing efficiency, we will get 74% space is filled. And each sphere is in contact with 12 spheres in this. So how the 12 spheres in tetrahedral, in hexagonal packing, closed packing and cubic closed packing, let's see. So in hexagonal closed packing, we will see here, see in the center atom, so it contains 6 spheres of its own, and 3 above and 3 below. So like this there will be hexagonal packing. And when we see cubic closed packing structure, again 6 spheres of their own layer and 3 above and 3 below. So total 12 is the coordination number. So it is the hexagonal closed packing structure, and it is the cubic closed packing structure. Thank you.